Alright, let's take a look at the first example of the chapter 13.1. We have a mass, looks like a crate sitting on the ground, and they tell us there is friction. I'm going to go ahead and draw friction in. If it's getting pulled to the right, we're going to call right positive, not because of that, just because of my convention. If it's getting pulled to the right, that means we're going to have a frictional force opposing the motion, so it's going to be going to the left. The force is 400 newtons and it's 30 degrees above the x-axis. Okay, so the first thing to do would be our free body diagram. Represent this as a mass. I try to go ahead and put mg pointed down right away. That means we're also going to have a normal force pointed up. And we have this force P, but we need to break that one into components so that we have P in the x direction and P in the y direction. It's going to be P cosine 30 and P sine 30. Okay, where this is 30. What else are we missing? Anything gravity and anything that's touching it's what I learned and what I'm trying to teach you. We still need to consider the friction. There's a frictional force going backwards. Okay, it starts at rest and they want to know what the velocity is in 3 seconds. We need to find the acceleration. And assuming it is a constant, we can use constant acceleration equations. If not, we'll integrate it. But first step, free body diagram. Second step, let's make out the equations of motion. And we do this independently. We sum the forces in the x direction and say that's equal to the mass times the acceleration in the x. And let's go ahead and do it. What do I have in the x? In the positive x, I have P cosine 30. And I have a minus f because it's pointed to the left. And that's it. And that equals mass times the acceleration in the x direction. If I sum the forces in the y direction, I get mass times the acceleration in the y. What we should really do is compare mg, which points down, with the component up, py or p sine 30. And when you do so, you see that mg, the weight of the block, ends up being around 500 newtons, whereas P sine 30 ends up being about 200 newtons. What does this mean? This means it does not lift off the surface. So, we do need to check that, right? If this lifted off the surface, we'd have a whole nother problem. We're not there yet, but still, we need to get in the practice of checking. Okay, so continuing summing the forces in the y direction right here. I have a P sine 30 going up. I have a normal force going up. Ding, ding, and then I have an mg going down. That equals mass times the acceleration in the y. Now since it does not lift, you can say this equals 0. Alright, this gives us two equations. One, let's call it A and B because I've already used 1 and 2. A into B will give you the acceleration, and then you can find the normal force. So I get 5.185 meters per second squared. That's going to be to the right, and we get a normal force equal to 290.5. The reason we needed the normal force too is this term right here, the frictional force is equal to the normal force times mu. They gave us mu, So replacing friction right there, we would put in, I think it was 0.3. Yeah, 0.3 times the normal force. So this equation would look like P cosine 30 minus the normal force mu k is equal to the mass times the acceleration in the x direction. Alright, and ta-da! What we find is this acceleration is constant. We know it's constant, it's not a function of time. It's just a number, it's a constant. So we can use constant acceleration to find its velocity. V final is equal to V naught plus the acceleration, in this case is the x direction, times time. Alright, they wanted to know after 3 seconds, so we can plug in our acceleration. It started from rest. V final is just going to be equal to 5.185, that's the acceleration, times the 3 seconds. And I get 15.6 meters per second I, or 15 meters per second to the right. The book typically isn't going to write the stuff as vectors. If it's just a one scalar quantity, it'll put an arrow. Practice using vectors. That's our future. Alright, yep, that's it.